himself after.
Wait. So what happened is he said E equals mc squared. He said E equals mc squared. And what they discovered was that some of the mass, so when he said E equals mc squared, the most astounding thing, hey, wait a minute. The most astounding thing he said was not that. It was not that. And it was not that. It wasn't energy. It wasn't mass. It wasn't the speed of light squared. The fact that he put these together was amazing, but the most amazing thing was this right here, the equal sign. He said energy is mass. Mass is energy. And so what was happening is you have this mass of the protons and neutrons. And when you get to be, atoms get bigger and bigger, they weigh less in a big atom. Well, what happened to their missing mass? And their missing mass is converted into energy, which holds them together. And that's when the nuclear bomb happened. They said, wait a minute, if that's true, then if we split that atom, there must be a lot of energy holding the nucleus together. A lot. Way more than dynamite. And it was. And that's when the nuclear bombs came about, the whole idea of nuclear energy. We have a whole chapter on that, yes.
So it says earlier that a sample of copper is vaporized. How exactly does one vaporize copper?
We have, in the gym, every time we turn lights on, they're really bright, aren't they? Brilliant. Those bulbs have vaporized mercury in them. That's why you don't want to break them, and you don't want to just throw them in the trash. But if you could change it into a gas and have very little pressure inside there, it'll stay as a gas. Now, if you were to break that bulb right away, it'd probably turn back into a liquid. So you have to heat it. You have to heat it and then put it into a container or into a chamber.
I just mean that I feel like vaporizing mercury would take something very hot.
Not actually, just the opposite. Mercury is dangerous because you can heat it a little bit.
Oh, I mean copper, sorry, not mercury.
That's a great question. I don't know the exact point where you start getting a lot of vapor off of copper. I don't know what the temperature is. I don't have to get to the boiling point to vaporize something. Like if I put water here at room temperature, why is there less water in there tomorrow? Did I reach the boiling point overnight? Can water vaporize below the boiling point? Yes. And so a piece of copper, if I heat it a little bit, some of it will vaporize, even though I haven't reached the boiling point yet. Yes?
So with the nuclear bomb, when the atom splits and all the energy that's holding it together is released, does the energy turn back into mass? Or
Okay, that is a fantastic question. Now, we actually do know how to change matter into energy with our nuclear reactions, okay? Unfortunately, we're not very good at going this back to this. Now, do we have evidence, though, of energy, of no matter being there, and energy, all of a sudden matter appears out of nowhere?
Yeah.
Well, there is a little bit of evidence that, so we know what happens. Now, on Star Trek, they simply order up. I'll take a hot tea, and all of a sudden they take energy and turn it into a cup of tea. So they're really good when that's why it's science fiction, but I certainly don't know why we couldn't in the future change energy into matter and organize the matter into whatever you want to organize it into. That's great thinking.
I hear that
There is evidence of doing this, but it's in the small world of all of a sudden a small particle appears.
so you could make whatever you wanted to.
It's true.
In theory,
With
you could make so many protons, so many neutrons. You can make so many whatever kind of atom you want, and then you could eventually put the atoms together where you want them to be? Yes.
So once any sort of atom turns into a liquid, turns into a gas, say you take away all of the atoms except one, how do you know what state that atom is in?
Well, that's a great question. I mean, to me, do you want to call that a solid, or do you want to call it a liquid? And I don't know if we can define that, because a lot of our definition has to do with if you're in a solid, how do you interact? How far away do you get from your next door neighbor? And that has to do, so maybe the definition of solid, liquid, and gas depends on there being a certain number of you. What a great question. You could say it's all of them, or you could say it's none of them. If your definition has to do with how they interact with each other, then it's none of them. That's a great question, Ann. I'm going to show you real quickly here. So what's confusing is this thing has a mass number of 63, but its actual mass is 62.93. Now, what we need to do is, if you look at the math here, you see that it says, let's see, where am I at here? Okay, it says here there are two isotopes. Okay, so we have this one that occurs 69.09%. I'm sorry, of the time, and this occurs 30.91. So to do a thing called a weighted average, you take the percent of the time that it occurs times the mass plus the other percent times its mass, and then you'll get a number. Now this number here comes out to be the average. So some of the homework problems that you're going to be doing, I don't see that one here. What should you get? If I say this isotope occurs this amount of time and it weighs this much, plus this percent it weighs this much, plus this percent it weighs this much, what number should you get? You should end up getting the number on the periodic table. So when you're doing your homework, if you look at that homework questions like that, some of them are very thoughtful. Some of them are actually challenging, very challenging. Yes? Well, right now, if I knew that there was a half day somewhere, but I may have to make it a week from Thursday if that's the case. I may have to do that. We'll see. I'm going to say the earliest it would be is a week from Thursday. Probably.
Is uranium as rare as something like diamond?
Is what now?
Like how rare is uranium found in the ground?
Okay, that's a good question. We've been all over the planet, but there are people still searching for oil, and they find all of a sudden, hey, I didn't know there was oil there, and they are very sophisticated ways of searching for oil, and they also do the same thing for uranium. Now, nowadays, they have to have some way that satellites can pick up a difference. So if the satellite is equipped with something that might be able to tell you what kind of radiation is being given off, then you might be able to spot places that have more uranium than other places. I bet there are places in Upper Canada that nobody's ever even been to that has probably uranium. Out to west, a lot of those states have uranium out there. Yes?
Is it usually, it's always found in solid form, right? Like you don't...
Yeah.
Okay.
And they have, it doesn't look very, it looks like a rock, like a gray rock.
I thought it would like be shining green and like.
No, the Simpsons make it look like. Now, what happens is radioactive material. We'll have another chapter on this, but you could have radioactive materials that give off radiation. It could make the air around them glow. So you could have something that would scintillate the air, like Madame Curie, and they had some that it was like they turned all the lights off and it would actually glow. It was actually scintillating the air around it.
Like radium?
Just like lightning. Lightning actually excites the air around it. You can't actually see lightning. What you see is the effects of lightning as it does things to the air around it. That's why lightning on one planet would be different than lightning on another planet. They wouldn't have the same color. All right. The next thing I'm going to do, this is probably one of the most important things. When you go to college, I want you to be so much better than almost everybody else. The next thing we're going to look into, and we've had this before, but you have to be really good at it. Now we're going to be using factor label here, and we're getting back into that a little bit. I have seen so many books, and they try to teach you the mole concept. I've seen, you can go online and look at this teacher made this mole wheel, and the mole wheel says, you want to change moles to grams, do this, and it has all these like 10 different things you do. You just have to remember all 10 of those things. And I don't teach it that way. I could. I remember when I taught at Grimsley, there was a really good chemistry teacher there, but he had made a mole wheel, and he just made his students, it's like the unit circle you guys have to memorize, right? He just made them memorize the mole wheel, but it kind of left them. I know that when they went to college, some of that left them. And I want to be with you forever, almost forever. So what I'm going to do is, I'm going to start out with this right here. What if you're an element? What is the mole concept that you want to do? Now, the mole concept was one of the biggest ideas in chemistry. It changed chemistry. If you want to know about chemical reactions, you really need to know how many particles are reacting with how many particles. Well, what SI unit is used to measure number of particles? The mole. And that's why it's one of the base units, the mole. So we know that mole, of course, is this many particles, 6.02. Some books say 6.022. Right now, that's about the only thing you might remember from 10th grade is like a dozen is 12, and 6.02 times 10 to the 23rd is a mole. Okay? So we're not going to argue that. What's a mole? You argue about why is a dozen 12? No, a dozen is 12, isn't it? So we don't argue about why is a mole 6.02. We can try to figure out how they got that number. So let's take a look at an element, all right? Let's do like sodium. And we start here. 1 mole of sodium equals. All right, I need you guys to be more engaged, okay? Parker, this is not going to work for me. This won't work for me. Okay? All right, what I'm going to do is, if you can learn the equivalence and you know how to do factor label, you will always be better than your counterparts at mole concept. Okay? You don't have to worry about mole wheel, stuff like that. This is going to work for you. 1 mole of sodium is equal to 6.02 times 10 to the 23rd. And the most important thing, what comes after there?
Atoms.
And why do you say atoms? Because the smallest piece of an element that still has the properties of that element is an atom of it. That's why it's atom. It's not because I just told you. The smallest piece of an element is an atom. Now, if you look up here, I noticed that I go over here and it says 22.9. Let's say 999. Is that what it says? So here, I'm going to put another one equals 23. I'll just round out to 23 because 22.999 grams. Now, what's interesting about this is that that number on the periodic table stands for 2 things, and I taught this to you before. I'm going to do it again. What is 1 atom? What's the mass of 1 atom of sodium on average? What's 1 atom of sodium? How much does it weigh?
1 AMU. Oh, 1 atom? 22 AMU.
22.999, which is 23, right? 1 atom of sodium weighs about 23 AMUs. Is everybody with me? Now, what if I gave you 100? Well, then it would weigh 2,300 AMUs. But what's interesting is, if I give you not 100, I give you a huge, huge number of these atoms. If I give you this many atoms, that's so many AMUs, it comes out to be what? 23 grams. And that's what people don't understand. That periodic table, in the little world, 1 atom is about 23 AMUs. But if I give you a mole of those atoms, it'll be 23 grams. Which world can you do chemistry with? The gram world. So whatever's going on in the gram and mole world, that's what's going on in the little tiny world also. And that's why the mole concept changed chemistry. Let's do another one. 1 mole. Parker, you do one. 1 mole of uranium. Give me the equivalence. Give me the equivalence.
6.02 x 10 to the 23rd atoms.
I made a mistake here. I should put sodium here.
Oh, well then I look at the chart. So, oh, you're right.
You round to 10th place if you want.
Pesky uranium. Oh, there it is. 238.
What?
238. Is that
238 what?
Oh, geez, grams of U.
Okay.
Yeah.
And Parker, how much would one atom of uranium weigh on average?
238 AME.
That's right.
Oh.
If I gave you 1,000,000 random uranium atoms, Parker, if I gave you 1,000,000 random uranium atoms, how many of them would have a mass of 238.029?
So if you have 1,000,000 atoms,
Yeah.
I guess that number.
What do you think?
I guess that would just be that number because one atom
What do you
is
think?
always just
How many?
that.
I'm a smart person. 0.
0. Because the number on the periodic table is actually, the number on the periodic table is actually the average mass, including all the different isotopes, but no one isotope has that mass. Take a look at hydrogen. There are no hydrogen atoms in the universe with that mass. There's some that have a mass of 1, not as many with a mass of 2, and very few have a mass of 3. Okay, let's keep going now. Now, what I'm going to do is, if you can remember this with the elements on the periodic table, then you could build this, and how many different conversion factors could you make from this equivalent? If I give you this equivalent, how many conversion factors could you make? Not infinite. What do you think?
3,
3? That's not enough.
6, 5,
What made you say 6?
Why would it be on?
Because you can do
8.
Wait, listen. Listen to people. What? All right, so let's call this A.
moles over atom.
Let's call this B. Let's call that C.
You can do
So an equivalent is something on top equals A on the bottom, right? So you could have what? A over
A over B
A over B
equals
and B over A. What else?
equals A over C equals C over A equals B over C
No way.
What is it?
B over C C over C.
And you're right, 6. Very good. Excellent. Now, so if I give you these 3 equivalents, you could build 6 different conversion factors, and factor labels should be no problem for you to do. But now let's go to the next one. What if I have a compound that is covalent? What if it's a covalent compound? Let's try this one. Let's see. Who wants to do this one? Marie. 1 mole of water.
Machine guy.
And how do I know this is a covalent compound? Wait, I can't. Hey, what?
Or the individual atoms will have charges.
But if I do this, I don't know if they have a charge because I didn't draw them, but
Oh, it's
how do I know this is most likely to be a covalent compound?
because it's non-metal.
Yes. Non-metal, they're going to tend to form covalent bonds. So 1 mole of water, keep going, Marie. What you got here?
Equals 6.02 times 10 to the 23rd molecule.
Okay.
Hydrogen is. Oh no, it's not.
Notice that we didn't say atoms because there's no such thing as an atom of water. And how do you know that? It's not on the periodic table of the atoms. So molecules of water equals, go ahead.
It's like the polar breakdown.
I really need you to concentrate, okay? You're not going to be here next couple of days, so let's concentrate a little bit. What do you think?
I guess 2 times the or the atomic mass of hydrogen.
Uh-huh. So 2 times 1.
Okay, so 2 plus and then
So 1 plus 1 plus 16.
yeah,
18 what?
18 grams.
Yes? Now, by the way, in every case, there's a special name given for this right here. What's the special name given for this column over here? What's this for sodium? What's this for uranium? And what is this for water?
Molar mass.
Yes.
Oh.
And molar mass is how many grams it takes to make a mole. Is that right? Is that right? Now, Marie, what about 1 molecule of water? How much would it weigh?
18 AMU.
Yes. Excellent. Everybody got that? Now, you could do the same thing. We could do the same thing with carbon dioxide or glucose and things like that. I'm gonna draw the line here, and let's go another one. Let's do a compound. Oh, I'll tell you what, I have one more over here. I'm gonna do one more underneath this one. What about this one? 1 mole, and this is where you have to be careful. 1 mole of O2. Okay. Rollins, you wanna do this for me? 1 mole of O2. Now, here's where we have to be careful in stoichiometry. If something combines with oxygen in the air, then that's O2, isn't it? And I have to use 32 for the molar mass of O2. But if I'm asking for how many moles of oxygen are in something like C6H12O6, I'm not using, I won't be using the 32, because that's oxygen atoms in a compound. You get that? So the mole concept would apply 16 grams per mole if it's in a compound, but if it's in this, like this, it's 32 grams per mole, isn't it? Let's do another one. How about a compound that is ionic? So let's do this one. Clayton, you want to do this one for me? Are you up to speed yet?
Yes.
All right, so 1 mole of NaCl equals
6.02 times 10 to the 23rd molecules.
okay.
For light of heat.
I'm gonna leave that blank for right now.
Uh-oh.
Sounds good. So it's 23 sodium
And
chlorine.
chlorine and copper. Please don't go to college and think that chlorine is 35. It's 35.5, and copper is going to be 65.5. Okay, they're not going to round off 0.5 or 0.49. So it's going to be 23 and 35.5. How many?
62.5.
Nope.
52.5. Oh.
Okay, so anyway, 23. Yeah, 23 plus 35.5 is 58.5 grams. Now, watch this here. And the only reason I left this blank, I didn't expect you to remember that from 2 years ago, okay? But when I was first learning this, it was so confusing to me. I know I didn't understand the concept of the mole. I was trying to copy what the teacher was doing, but I didn't understand the concept. And I'd read the book, and it said something about this and atoms, and said, I think I got it. I think I got it. And then I turned the page, and after Avogadro's number, they didn't use the word atom. They used the word molecule. I thought, whoa, I guess I don't have it. I thought you always put atoms after Avogadro's number, and you don't. And then I said, okay, now eventually you figure this out. And then I turned the page, and then formula units. Whoa, I had no idea what they were talking about. Why did they all of a sudden, after Avogadro's number, they started using something else? And the smallest piece of an element that still has the qualities of that element is an atom. The smallest piece of a covalent compound that has those properties is a molecule. Now, I'm not saying I've never seen a book that called these molecules, but they shouldn't, because there is no molecule there. It's an ion and another ion. And there's no covalent bond between them. It's just the ions are attracted to each other. Get that? The perfect name, I wish they would have asked me. The perfect name would have said, I would have called them ionic units. What's an ionic unit? 1 Na, 1 Cl. What about for barium chloride? 1 Ba and 2 Cls. That's an ionic unit. That's a great name. Somebody way before me called it a what? Formula unit, and I can't change it. And I told you in 10th grade, and in 10th grade you would giggle a little more because you were 10th graders, but I said I don't like formula unit because when you abbreviate it, I just didn't like writing that abbreviation. Gee, wait a minute. I didn't understand that. I didn't understand that in the 10th grade, but now, wait a minute. Okay. So now, all I'm trying to tell you is that if you know these equivalents, there is no mole problem that you shouldn't be able to do. So I'm gonna give you, let me see what time it is. Okay, I'm gonna give you a couple mole problems, and you can sit next to your partner, and we're gonna see if we can get these right. I'm gonna make them up on the fly.
Is our partner just the person sitting next to us? I completely forgot about that.
All right, let's try it. The first one I want you to do is this one, and you have to show your work. You have to show your work using factor label, and I'll make up another one in just a minute here. All right, everybody find a partner and need to do these problems. First one, 60 grams of glucose equals how many moles of glucose? That's a warm-up problem. You should be able to do pretty well on that one.
I'm just kidding.
And then the next one, much harder, 850 atoms of calcium equals how many moles of calcium?
I feel like the second one is way easier than the
Okay, then
Oh, you
we'll
think
do the
so?
second one partner.
Okay.
We're gonna need to
Hey, yeah, you show us guys.
Y'all's guys.
Y'all's guys, this is, don't worry, I have my own. I come strapped.
Brad.
Strapped.
Do you want to be my partner, Parker?
Yes, partner.
My calculator is not.
Partner, do you need a calculator?
Let's start with the second one.
The second one.
Start with the second one because it's easier.
So, C.
You know
That's
that
12.
All right, do you want to make the second one harder?
No.
Let's make the second one harder.
you don't have to.
Let's make the second one harder.
I'm sorry, I didn't mean. I'm sorry, guys, I didn't mean to.
I don't know what he means by him, you know.
All right, here we go. All right, let's make the second one harder.
You do the second one. I do the I do I just do the first one. So 12.
We have about 4 minutes. If you can get these done, I'll feel pretty good about when you're getting ready to leave here.
12.
So mole mass is 185.
So 60 divided
6 times 16.
Can you read?
So we do 6.02 times 10 to the 23rd is goes on to 185.
Calcium is 40. Just 40.
Just 40.
It's just 40.
Wait, right?
So, I think I did this right.
It's H12, not H6.
I got 100.
Oh, it's H12.
That's right. Well, not moles.
Or not moles, but. Oh, yeah. Moles. Oh, it's moles. When
What's-
you label it.
Okay, what's your equivalent? 1 mole of glucose equals 6.02 times 10 to the 23rd what?
Oh, is that molecules?
Molecules equals how many grams?
I thought you. I see where you crossed it out, so it's just MOL.
I
No,
got the answer.
no, this isn't. This is moles.
Oh, that says
You got
moles.
number 2 yet, Mr. Kenny?
Oh, I'm
No,
not.
I made them ahead.
I'm not doing.
What I'm asking is, if you can come up with the 3 equivalents, then you can build this conversion factor. 1 mole of glucose equals 6.02 times 10 to the 23rd molecules of glucose. I'm not going to use that. Equals how
I
many?
got the grams.
That's right.
Yeah, so then 180, and then that gives you.
Okay, so now,
Yeah.
all right, did everybody get 0.333 moles?
Yes.
Okay. The second one is every time I've given a test, every time I throw an AMU question in there, that's the one they tend to miss because they weren't paying attention or they didn't understand that that number up there stands for 2 things.
Grams.
All right. Yes. I don't have the answer. I just made it up. But
So I converted AMUs to atoms.
okay, hang on.
Slow down.
Now, in order to do that, though, you would have had to have
I converted
AMUs and atoms, right? What did you use here?
40.
40. Wait, 40 AMUs.
Yeah, 40.
All right, so 40 AMUs equals what? 1 atom.
Of calcium.
I like that. Okay, there's that. Now, then what?
Oh, then you have to convert to moles, and 1 atom, or sorry, 1 mole is 6.02 times 10 to the 23rd atoms of calcium.
That's very good. Now, the only thing you might make a mistake. Your thinking was great, But you remember, whenever you have a scientific number in the denominator, you have to use parentheses. If you don't, the calculator will divide by 6.02, but then it'll throw the 10 to the 23rd in the numerator, and you'll be off by 46 powers of 10. So make sure when you divide by a scientific number, you put it in parentheses,
Or
okay?
you can divide by 6.02 divided by 10.
Yeah. Could do that.
And they say you can
Hey,
have
good idea,
books
son.
and-
All right. I don't know what the answer is, but you know what I'm really interested in? Did everybody set the problem up right?
Yes.
Yes.
Okay, so you knew that, so 1 atom of calcium is 40 AMUs. All right, hey, listen, let me say something, I'm gonna turn this off.